Good afternoon, everyone. I'm Bhoomika, and I'm working as a postdoctoral fellow with Lessons. So today I'll be talking about gamma ray emission from active galactic nuclei. So I'll start. I'll start with the general introduction of normal galaxies. In this picture, we can see the normal galaxy with spiral arms. The emission or the most of the radiation we get from the normal galaxy are mainly produced by the stars which are present in the galaxy. So we see the spectrum in the optical, IR and UV range, which is generally the individual stellar spectra, and we get the absorption line, which because most of the stars produce absorption line in the normal galaxies. Now coming to the active galactic nuclei or AGN. So we can see from the name only that its nucleus is very active. So the most of the emission which is coming from the active galactic nuclei, which is coming from the center of the galaxy. So the center of this galaxy is the very powerful region, and this emission cannot be directly attributed to the stars. So the this powerful emission we get from the active galactic nuclei, so it is believed that it originates from the accretion onto supermassive black hole. So in this picture, we are seeing this yellow ring around this is the supermassive black hole, and the yellow ring around the supermassive black hole. So this ring is known as the accretion disk. Now, what is accretion disk? So accretion disk is the black hole, the material from the dense star filled galactic core, or where the stars are present, they are falling into the black hole region. So as stars and gases are drawn into the black hole, so they start accreting around the black hole, and they make accretion disk. And also some of this amount of gas and stars comes out in the form of jet. So this jet covers the full energy range of the electromagnetic spectrum. These are the jets which are coming out from the active galactic nuclei. So these jets cover the full energy range of the electromagnetic spectrum, that is from radio to gamma ray. Now this is general cartoon picture of active galactic nuclei. This is the central black hole. This is the accretion disk around the black hole. And the other component also, where this violet region are the broad line region, which is up to 0.1 parsec. After that, this is the dusty torus. This is found up to 1 parsec or 10 parsec. After that, this green region are narrow line region, and their range is up to 10 parsec or 10 to 100 parsec, this narrow line region. And these are the jets which are coming out from the central region, and they go these jets go up to the range of kiloparsec or megaparsec. And if these are the different view of AGN, which I'll talk in the next slide. So different view of AGN. This is the A-zone view. If we see this A-zone view, like in this picture, we are seeing in this direction from here. So these jets are at the 90 degree angle from us. So this, what we see here, we generally see the radio lobes. So these are AGN, but radio lobe galaxy are one part of AGN. In this view, we get this radio lobes which are up to kiloparsec or megaparsec from the central region. And this is the another view of AGN. We are seeing at some, like we are seeing from here at some angle from the jet. So if we see this angle, we can see this jet as well, and we can also see some central part of this galaxy. So these galaxies generally we see at some angle. These are called Seyfert galaxies. Seyfert galaxy, like here I have shown that if we are seeing in this direction, these are the Seyfert 1 galaxy, and if we are seeing in the direction of Taurus, these are Seyfert 2 galaxies. Now the another view of AGN, if we are looking down directly into the jet, so this jet we are seeing directly into the jet. So this kind of, when we see in this direction, so this kind of AGN are known as blazars. So because we are getting the radiation now directly from the jets, so we get the full electromagnetic radiation, and mainly we get this jet produce gamma ray and X-rays. up to the range of X-ray and gamma ray. Now, if I talk about the gamma ray emission in the universe, so gamma ray emission, generally universe is transparent for the gamma ray emission, but Earth atmosphere is opaque for the gamma ray. So we need space-based telescope to detect the gamma ray emission in the universe. So as if we take any low Z material, so gamma ray will pass through that material, but so we cannot take that material as a detector. So we take some high Z material to detect the gamma rays, and we have this different detection mechanism: Compton spectrum, electron-positron pair production, and the photoelectric effect. From these methods, we detect the gamma ray. Now, currently the main telescope, the main space-based telescope, which is observing the gamma ray in the universe every minute, every second, or every moment. So this is the Fermi Gamma Ray Space Telescope, which was launched in 2008. So till now, Fermi has identified around 5,000 gamma ray emitting sources, and 3,000 among this 5,000 AGN or active galactic nuclei, 3,000 of blazars have been detected. Now the Fermi Gamma Ray Space Telescope has two main instruments. First one is LAT, which mainly observe the gamma ray emission. The LAT is large area telescope, which observe emission in the range of 20 MeV to up to 1 TeV. And another instrument is GBM or gamma ray burst monitor, which detect gamma ray in the range of 8 keV to 40 MeV. And this instrument mainly works on the principle of electron-positron pair detection. The gamma ray falls on the detector, which is tungsten in the Fermi telescope, and it converts into electron-positron pair, and they pass through the material. So this is the sky view of sky map of Fermi. So Fermi, before Fermi, its predecessor, which is EGRET, Energetic Gamma Ray Experiment Telescope, it has not identified some of the bright blazars. So it has identified by Fermi. The one source is PKS 1502 plus 106. So this was observed by Fermi, and also the very bright source 3C454.3, which is found 5 times brighter than the which EGRET has measured in its era. Now, Fermi, what is special about Fermi? So we know that gamma ray are the most powerful form of light, and they generate in the extreme condition. So through Fermi, as it studies the gamma ray, so we can study the powerful emission process and the exotic phenomena which is producing the gamma ray in the universe. And Fermi has the main point that it scans the sky in every 3 hours. So it has large field of view, and it has large effective area. So that's why we get the full sky coverage in 3 hours, and also we need this because gamma ray sky showing variability in the range of from minute to year, short-term time scale to long-term time scale, which is from millisecond to years. So that's why Fermi is providing very important tools to study the gamma ray, as well as its variability up to from short term scale to long term time scale. Now I'm coming to the blazar, which are the most important source which emit gamma ray in the universe. So blazars, it is a class of AGN, which is most spatial and luminous persistent class of in the universe. They are compact radio sources. Compact radio source, its central is very compact, and they are mainly hosted by elliptical galaxies. Blazar belong to jet-dominated class of AGN because we have in normal galaxy we have total 10% of AGN, and in this 10% of AGN, only 10% of AGN produce jet. So blazar come in the jet-dominated AGN. So they emit relativistic jets, which is pointed close to the absorber. And blazar, as this jet are pointed close to us, so they show flux variation in the entire electromagnetic spectrum, that is from radio to gamma ray. And they are also, because in optical spectrum, in optical emission, they show highly variable polarization. Now blazars are further divided into two classes. First one is flat spectrum radio class, radio quasars. Second is BLA objects. So the difference between FSRQ and BLA, FSRQ is flat spectrum radio quasar. We in the optical spectra of FSRQs, we get the emission line, where the equivalent width of this emission line is more than 5 angstrom. Whereas in BLA object, we don't observe emission line, or either it is too weak, and the equivalent width of these lines are less than 5 angstrom. So these are the two example of, this is FSRQ source 3C273, its optical spectra, and this is BLX source PG1553, where its optical spectra is shown. Now coming to the spectral energy distribution of blazar. So spectral energy distribution, where we see the, because in blazar we are detecting the fully electromagnetic spectrum from radio to gamma rays. So in the SED of blazars, mainly two components are there. Low energy component, which covers the energy range from radio to UV or soft X-ray. Second one is high energy component, which covers the energy range from X-ray to gamma ray, or it goes up to TeV gamma rays. So here I've shown the two SED of FSRQ source, and this is for BLX source. This is the low energy range, which is covering from radio to UV, and this high energy range is coming in the X-ray and gamma ray. And this is the BLX source, which is where the low energy emission is covering the radio, optical, and X-ray, UV X-ray, and this one is the gamma ray. So the difference between the SED of blazar is the, we can see here, which I will explain why this difference is there in the FSRQ and BLX. Here this high is more than, I mean, the peak is going more than of the low energy emission, but here it is lower than the low energy emission. So this can be described through the source of energy emission in blazars. So because blazars are mainly dominated by the jet, so jets are the main component of jets are lepton and hadron. So we define the energy emission in blazars through leptonic model and hadronic model. So in leptonic model, the low energy emission comes from the like leptons are what, electron and positrons. So that relativistic electrons are present in the jet, and they produce synchrotron emission in the magnetic field. So that's why we get the low energy emission in the jet, from the jet, and high energy emission we get through the inverse Compton. So inverse Compton process is where low energy photon gets scattered through the electrons, this relativistic electrons, and they produce high energy emission. So again, the difference in this these two classes of FSRQ and BLX. So first one is SSC is the synchrotron self-Compton. Synchrotron self-Compton is where the photon which are produced through synchrotron emission, the low energy photon which are produced through synchrotron emission, they only take part in the inverse Compton process, and we get the high energy emission. So that's why the SED of this BLX source, this is the emission produced by synchrotron self-Compton process. But in FSRQ, this low energy photon which can gets scattered through the relativistic electrons, they can come from the outer part of the AGN, like accretion disk, broadline region, or torus. So that's why this in FSRQ source we get this peak. This is because of the external Compton, where the low energy photons are coming from the outer part of the active galactic nuclei. Now the hadronic model. So hadrons are the more heavy particles, which are mainly protons. So as we get the low energy emission from synchrotron emission process of the relativistic electron, so in hadronic model also we get the low energy emission from synchrotron emission process from relativistic electrons, but the high energy emission which comes through the synchrotron emission of the protons. So that is the difference between these two models. So in leptonic model, the high energy emission is coming because of relativistic electrons only, but in hadronic model, the high energy emission is coming from relativistic protons. So that's why in the till now we don't have clear view that how this gamma ray emission or high energy emission is coming in the blazar. Whether it is, so the main question here comes that what is the cause of this gamma ray emission in blazar, whether leptonic is responsible or hadronic is responsible. So this can be studied via two approaches. First one is via SED modeling. SED modeling is like we get the full data from radio to gamma ray, and we can we can check the SED. But for that we need good model, and we also need good simultaneous data which is covering all the wavelength. The other possible approach is the correlation study between optical and gamma ray. This is because as I told in the last slide, the low energy emission and high energy emission in leptonic model both are coming through relativistic electrons. So if we see the correlation, if they are correlated, the variation in the optical and gamma ray are correlated, then we can expect that leptonic model is responsible to produce this emission, high energy emission as well. But if we don't see any correlation, because in hadronic model, the high energy emission is coming because of relativistic protons, and low energy emission is coming because of relativistic electrons. So we don't expect that we should see a correlation between them. So this is another possible approach to study the high energy emission. Now to taking this second approach, that where we wanted to study the correlation between optical and gamma ray as or low energy and high energy. So we took a sample of the Fermi 3FGL catalog is the third catalog of large area telescope. So we took that 3FGL catalog where around 11,000 blazars are studied, are detected. So we generated 1 month wind gamma ray light curve for the period of 9 years, and we looked for the at least if there is one flare is present more than 10⁻⁻6 photon per centimeter square per second. Now we want to study the correlation between optical and gamma ray. So we also looked for the optical data, simultaneous optical data, which is we have taken, which is present, which is available archival. So from Steward Observatory and from SMARTS, which is overlapping the gamma ray data, the same data range, optical data we took from Steward and SMARTS, and we finally got the 8 blazars where 5 FSRQ and 3 BLA. We got good overlapping data in the optical and gamma ray. These are the sources. These 5 are FSRQ sources: 3C454.3, this PKS 1510 minus 0.89, and yeah, these are the 3 FSRQ, and the OJ287, AO0235, and PKS 2155. These 3 are BLX sources. These are the RADEC and redshift of these sources. So I'll show the example of one FSRQ source here. So what we have done here, we plotted the multi-wavelength light curve for this source, for the period of 2008 to 2017, for the period of 9 years. So here in first panel, what we have plotted, this is the one-day binned gamma ray light curve, which is taken from which is generated using Fermi data. And then in second panel, this is the X-ray light curve, which is generated using Swift. Swift is also a space-based telescope which observes the X-ray. So this is taken from the Swift data. And in third panel, this is the optical light curve. Where the data is taken from Steward and SMARTS. In the fourth panel, this is the IR light curve which is taken from SMARTS in J and K band. The last panel, the polarization degree in the optical band, which is taken from Steward. Steward also provides polarization in the optical V band, so that we have plotted in the slide. So what we looked here, any flare in the, whether it is in the gamma ray or in optical. If any flare is there, we looked for the corresponding other flare. So we found many conditions, like gamma ray flare is there, but optical flare is not there. Or same other condition, we found that optical flare is there, but gamma ray is not present. So I can here like this epochs, when I plotted in the zoomed version, these are the zoomed version of first two epoch. Like I plotted this line. So these are the zoomed version of this epoch. So in this first epoch, we can see this is the gamma ray. This gamma ray flare is there, but optical is flat. And in second epoch, where the optical is flaring, but gamma ray is not flaring. So for these two different situations, we plotted the SED. These are the SED of these two epochs. So this looks same, but the difference in the parameter, where the low energy emission, this is the synchrotron emission. This emission is coming from accretion disk, and this is the high energy emission, which is coming from the external Compton, and this is synchrotron self Compton, and the same is for epoch B. Now the one more example of BL source, which is PKS 2155. So here we found two epoch. In one epoch, when optical and gamma both are and quiescent, means both are not flaring, they are just flat. And in second epoch, both optical and gamma ray flare is there. This this slide curve is also for the 9 years, for that from 2008 to 2017. So for this two epoch, when we generated SED, so as this is BL source, as I told that high energy emission is mainly dominated by synchrotron self Compton. So we found that gamma ray emission is mainly coming from the synchrotron self Compton, and the low energy emission is coming from the synchrotron emission. So what we found in this study, we found different correlated behavior between optical and gamma ray flux variation. We found different when optical flare is there, but gamma ray flare is not there. So as optical is mainly coming off synchrotron, so in this condition we found that magnetic field has increased. So because of as magnetic field is increased, there is increment in the optical flare. But as the gamma ray is coming because of the inverse Compton, and inverse Compton is independent of magnetic field. So we didn't find any change in the gamma ray. And we also found the case where gamma ray flare is present, but optical flare is not there. So again, in this condition, we found that the bulk Lorentz factor, where the inverse Compton is mainly dependent on the bulk Lorentz factor, that has changed. Because of that, gamma ray flare is, we found the gamma ray flare, but we didn't find any change in the optical flare. Now we have total 5 FSRQ sources. So in 3 FSRQ sources, we found that optical emission is mainly coming from the accretion disk. It is not dominated by the jet. And the other 2 sources, we found that the optical emission is mainly dominated by synchrotron emission from the jet. And this 3 BLX sources, in 2 sources, A00235 and OJ287, these are where gamma ray is mainly dominated by the external Compton, and the one source PKS 2155, gamma ray is mainly dominated by synchrotron self Compton. So as in the initial, when we wanted to check the yes sir. Yeah. 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 We,
so because the optical will be reprocessed in that's the reprocessing emission which is happening.
Yeah. Yes, sir.
Okay. So here you are seeing in that case that what's the time lag you typically?
Actually, not. I mean, we studied time lag only for this source, because for other sources we don't have good data, enough data to study the time lag. So in this we found like for some epochs we found 0 days, for some 2-3 days we found the time lag. 0 also we found.
So how can it match? Because if one is basically a reprocess radiation, there should be a time lag, right?
But yeah.
Because I was thinking in the context of like the aggressive hadronic model, because that like so people may be missing that because every focus is
Left.
on SED mode like mostly.
Yeah.
So if it could be like we are seeing some interesting signature in another band,
Yeah.
optical or UV, which people may not be looking at, right? I mean, so that is where the careful analysis of the time lag or other features, let's say some spectral lines, I don't know. I mean, I rarely see papers where people looking to fault lines primarily. So that aspect also could be looked into to address the model.
Yeah.
That context from here thinking about.
Yeah, the thing also, like I will tell in the last slide, but that now neutrino has been observed. So neutrino is the direct evidence of hadronic component that is present in the jet.
But that is rare, right?
But still that till now it was only that we thought only that there is hadronic component, but now. So initially, as we studied we generated the gamma ray light curve for 1100 of blazars for 1 month wind. So further we studied the gamma ray flux variability of these blazars. So we have already the light curve from of this 1100 of blazars from 2008 to 2017. So where the 639 sources are BLX and 481 are FSRQ sources. So as we generated 1 month wind gamma ray light curve of this blazars, and we wanted to check the flux variability of this. So we calculated flux variability using excess variance of all the sources. So what we found here, this is some light curves. I'm just showing for the example that's how we plotted. These are the 1 month wind light curve of some of the sources. And yeah, so when we calculated flux variability amplitude and also we calculated variability time scale. So at variability time scale, like at what time scale source is showing variability. So this is the for all FSRQ, we plotted the distribution for FSRQ and BLA, and this is variability time scale. We plotted the distribution and we found that here, the main thing we found that more than 50% blazar are variable in the gamma ray. And in the sample of 639 BLX sources, 304 sources which are variable BLX, and out of 481 FSRQ sources, 371 FSRQ are variable. So we found that FSRQ are more variable than BLX in gamma ray band. So the overall conclusion of this work is, so we found that varied correlation between optical and gamma ray flux variation. So initially we thought that through different correlation behavior, we can if we get any difference between the SED, but we didn't find any difference that all SEDs, whether it is optical without gamma ray or gamma ray without optical, we found that all the SEDs are well explained by leptonic model only. And in the other work, we found that FSRQs are more variable than BLX. So the overall thing that only by studying the optical and gamma ray flux variation, we cannot constrain the leptonic model or hadronic model, which is responsible for the high energy emission. So here, like now in 2017, when this neutrino detection from blazar TXS not 0506 plus 056. So here, so because the neutrino is coming from the proton synchrotron, so we get the direct evidence of hadronic component in the jet. So to constrain the leptonic and hadronic model, we need a good simultaneous data over a large period, and also for large number of sources. Then only we can constrain the leptonic model or hadronic model in blazars. Thank you.